This is week 11 of the thermodynamics course. In the previous weeks, we saw about mixtures of gases, and then we went with psychromatic processes, which involves both water vapor and air. If you see in the previous weeks, we saw gases which don't react, chemically react. Uh, so in this week, we'll see a reaction process and the process involved in that, and we'll see some numericals based on that. So simplest example is your engines where you have petrol, you have combustion happening. So that's reaction. You send in fuel, you send in air. There's a mixture of components, and they combust, and there's a reaction happening. And in that process generates heat, and we'll see. We can estimate what is the calorific value of the fuel. So we have numericals on those. So we'll see how to solve this. So proceeding with that, going to the first problem, a dry analysis of the products from the combustion of methane with air is as follows. So you are doing combustion process of methane and air and fuel mixture. So methane and air, so you are combusting that, and that gives you CO2, which is 9%, CO, which is 2%, oxygen, which is 2.11%, and nitrogen, which is 86.89%. This is by volume. Now calculate the excess air equivalence ratio and the dew point temperature of the products, assuming the pressure to be 100 kilopascal. So if you see, we know the reactants when they have also given the products. So the reactants is your methane and air, which is reacting together. So that is the reactants. The products which is forming out of this is, you have they are saying it's dry analysis. So if it's a dry analysis, then there is no water. You have, so there will be water also forming. So because in methane you have is CH4, so you have hydrogen, you have oxygen, so there can be formation of water. So this being dry, so you don't take water here. So the products is carbon dioxide, which is CO2 9%, carbon monoxide CO, which is 2%, and your oxygen, which is 2.11%, and you have nitrogen, which is 86.89%. So if you see the total of all this mining is will be 100%. So this is given in a percentage of volume fraction, volume of ratios. So you need to find out how much is the excess air which you are providing, the equivalence ratio, and then the dew point when your products are at pressure of 100 kilopascal. So we'll see how to solve this. First, the problem it's given as the fraction which they have given is in volumetric basis. So we can, that is equivalent to your molar basis. So we can take volume fraction as equal to mole fractions. So then we can neglect water vapor. So because this is a dry analysis which they have given, so there is no water vapor here. So if you assume 100 kilomoles of dry products.
Good evening, sir.
Good evening.
Okay. Please continue.
Yeah, I've just started. So okay, I'll just give you the question. What is there then? See,
Sure, sir. You just
yeah,
continue. As you continue, I will check. No problem, sir.
okay. See, it's to. I'll start. Say the methane and air you're combusting, and the products are given in volume fractions. So you need to find out excess air, how much you are giving, and equivalence ratio and dew point. So that's the question. So because this is given in volumetric basis, that is equivalent to your molar basis. So the volume fraction you can take it as mole fraction, and then this being dry basis, you don't need to consider water vapor. So based on that, if you assume that we have 100 kilomoles of dry products, so because 100%, so we are taking 100 kilomoles, can to take all in the given values instead of some decimal values. So we have taken 100 kilomoles of dry products, then a kilomole of fuel, A kilomole, so and B kilomole of air is taken, because we need to find out, we don't know how much amount of fuel and how much amount of air is taken. So if you write an combustion equation, so A moles of methane is taken and B moles of air is taken. So air, if you see, you consider majorly it contains of nitrogen and oxygen. So oxygen 1 mole and nitrogen contains 3.76 moles. So nitrogen doesn't take part in reaction, so but it will get heated up, so it will take some, absorb some amount of energy. So A moles of methane plus B moles of air gives you 9 moles of CO2, because the volume fraction is 9%, and we say that it is equal to your mole fractions. So 9 moles of CO2 plus 2AH2O plus 86.89 of nitrogen plus 2 moles of carbon monoxide and 2.11 moles of oxygen. So if you do an carbon balance, so if you have all carbon atoms which is there in reactants will be equal to what is there in the products. So you are not, that is, there will be no this like mass balance. So if you see how much amount of carbons is present in the reactants equal to the that is present in product, so A into C, so that is there in the reactant, this will be equal to 9 plus 2. So if you see 9 plus 2, that's the amount of moles of carbon present in the products. So your A will become 11. So you will use 11 moles of methane. Similarly, you can do a nitrogen balance. If you do a nitrogen balance, you know how much amount of nitrogen is present. So 86.89%, so moles. So this will be equal to B into 3.76. So you divide by 3.76, you will get B as 23.11 mole. So now we can write the whole equation. This will become that you use 11 moles of methane reacting with 23.11 moles of air, which will give you the same amount of products which I have mentioned, and you get 22 moles of water. The analysis, you didn't use water, but the reaction produces water. The product analysis which you are saying to sampling, see how much, what all the component presses, there you are not using water. So then from here we know how much moles of air we have used. So from this we can find out the air fuel ratio. So if you find out air fuel ratio, mass of air divided by mass of fuel, or in terms of moles, if you have moles of air divided by moles of fuel. So air, if you see, air contains 1 moles of oxygen and 3.76 moles of nitrogen, so 4.76 addition into 23.11. So that is the number of moles of air which is there in the reaction, and 11 moles of methane, so divide by 11. This will give you 10.06 kilomole of air per kilomole of fuel which is being used. So for complete combustion, so this is the reaction which is happening in the equation. If it happened with the stoichiometric ratio, then what will be the reaction be? So if you write an stoichiometric equation, so this is all we will get. So that is giving a complete combustion. So there is no formation of carbon monoxide. So it will have only carbon dioxide, water and nitrogen. So this gives you a complete combustion, and you don't have any excess oxygen. So in this case, if you see, we have methane plus 2 moles of air, and then it forms a carbon dioxide, H2O, and then nitrogen. So this gives you, from this you can find out the stoichiometric air fuel ratio. So stoichiometric alkyl ratio is 2 into 4.76 divided by 1, because there's 1 mole of methane which we are using. So that gives you 9.52 kilomoles of air per kilomole of fuel. So now we can find out how much excess amount of air which we have given for the equation, for the reaction. So you need only 9.52 kilomoles of air for combustion, complete combustion, but you have supplied 10.06. So this air fuel ratio says that how for per mole of your methane, how much amount of air which you have supplied. So for this complete combustion, you need 9.52, but you have supplied 10.06. So the percentage, if you take between these two, that will give the excess amount of air which you have supplied. So that is equal to 5.67%. Next is to find out the equivalence ratio. So equivalence ratio is nothing but your stoichiometric ratio divided by your actual mass fuel ratio, mass of air by mass of fuel. So that gives you 9.52, which is the stoichiometric air fuel ratio divided by your actual air fuel ratio. This is 10.06. This gives you 0.946. Next is so we have found out your excess percentage of air and your equivalence ratio. Now we need to find out the dew point temperature. So to find out dew point temperature, we need to find out the only product which will condense first is your water. So the dew point is the dew point temperature of water. So for that you need to find out what is the pressure of the water vapor present in the product. And in the problem they have given that the product is the product gas, the complete gas is at 100 kilopascal. So your partial vapor of water vapor is your mole fraction of water vapor into your total pressure. This is Dalton's partial pressure. So this will give you you have 22 moles of hydrogen, water. So 22 divided by the total number of moles which is present. So 22 divided by you can take 100 plus 22, because in the dry gas analysis that's what we did. We took 100 kilomoles of the dry products. So you can straight away write 100 plus 22, or if you add up you will get the same equation. So into 100, so this will give you 18.03 kilopascal. So corresponding to this pressure, from the steam table you can find out what is the saturated temperature, and that will be coming around 57.8 degrees Celsius, which is your dew point temperature. So your dew point temperature will be 57.8 for 100 kilopascal of pressure of product. Any question in this? Okay. Next question is Indian rice husk biomass fuel has the following percentage composition on a mass basis. It has carbon 35, hydrogen 5.5, nitrogen 1.53, oxygen 36, and sulfur 0.08. It is burnt with 185% theoretical air, with air at 298 Kelvin and 100 kilopascal, and 75% relative humidity. Determine the required mass flow rate and air per kg of fuel, and the change in the dew point temperature of the product as a result of the humidity in the supplied air. So we need to find out how much air is required, and stoichiometric, and then what is the change in dew point temperature because of the humidity, and assume the sulfur in the fuel to be inert. So here nitrogen and sulfur both will be inert. So if you see the composition of 100 kg of fuel on a molar basis is given like in the table. So we'll see how to solve this. So your fuel contains all these 5 components with corresponding number. So you can express the fuel like this. So C contains 2.91667 moles of carbon. into which hydrogen 5.5, nitrogen 0.1093, and oxygen 2.25, and sulfur 0.0025. This is what is given in the problem. And then it is combining with air. So first we'll consume first we'll see uh, dry air without taking into account the humidity of the air. So in that case, if you write an combustion equation and you do a carbon balance and uh, similarly nitrogen balance, your oxygen balance, you need to this thing, you can find out the individual mole fractions, total moles of the reactants and products present. So this is how it will look. So this is your stoichiometric equation, complete combustion equation. So this is how it will look. So it will take for 1 mole 3.1667 moles of air, and your products which are forming is 2.917 of moles of carbon dioxide, 2.75 moles of water, and 11.96 moles of nitrogen, and your same oxygen is the same, sorry, sulfur is the same amount which is present in your fuel. Now in the problem it is given that you are taking 185% of the theoretical air, or the air required for complete combustion. So you are taking 1.85 times. So this will give you similarly same combustion products, plus you have excess oxygen and nitrogen present. So previously you had uh, this combustion, plus you have 0.85 times of oxygen which is not taking part in combustion, and then similarly the same part of nitrogen in the air present. So it's getting added up here. So now we know the complete equation. We need to find out uh, the required mass flow rate and the dew point temperatures. So first we will have to find out the change in dew point temperature. So we need to find out when it was a dry air, what is the dew point temperature. So just like in the previous problem, first we will find out the partial pressure of your water vapor. Then so in this case you have 2.75 moles of water present. So that divided by the total number of moles of the products. So you have to add up all the moles. So 2.9166 plus 2.75 plus 0.025 and so on, the oxygen and nitrogen. If you add up, you'll get 30.44275. So that is the total number of moles of present in the product. So into 100 for 100 kilopascal of pressure, which is given in the problem. So 100 kilopascal. So this will give you your pressure, partial pressure of water is 9.033 kilopascal. So corresponding to this pressure, from the stream table you can find out what is the saturated temperature, and that is 44 degrees Celsius. So this is what the dew point temperature is if you take dry air for combustion. So now so with the given data, the partial pressure of water vapor supplied in can initially is 0.75 into saturated pressure at 298 Kelvin. So because your 75% relative humidity and your air present at 298 Kelvin, so your pressure corresponding to that is 2.37675 kilopascal. So this is nothing but what we did is relative humidity is nothing but P by P saturated. So P saturated at 290 Kelvin into your relative humidity, which is 75%, 0.75. So that gives you 2.37675 kilopascal. So now the mole fraction which is present is 2.37675 divided by your pressure. So again Dalton's partial pressure. So from there you can find out the mole fraction of water vapor present at the inlet. So this comes out to be 0.0237675. So assuming that the ratio of the mole fraction of nitrogen oxygen in the air remains at 3.76, so your what will be the now the air's mole fractions. So you have oxygen and nitrogen, and their ratio of oxygen and nitrogen remains same. So oxygen and nitrogen, for 1 mole of oxygen, you have 3.76 moles of nitrogen present in air. So you're combining both, you can write in terms of oxygen as 4.76 into mole fractions of oxygen plus your mole fraction of water which you have found out. So this will be equal to 1. The summation of all air components in the air is equal to 1. This mole fraction, summation of mole fraction is 1. So from this you can find out your mole fraction of oxygen, which is 0.2051, and your similarly for nitrogen it is 3.76 times of 0.2051. So for each mole of oxygen in the humidad, you have 3.76 moles of nitrogen, and your mole fraction divided by oxygen, so that gives you 0.11588 kilomoles of water vapor. So now the new equation taking into the moist air, so you have the same fuel plus 1.85 times of air into the number of moles of air required for combustion into you have oxygen, 1 moles of oxygen and 3.76 moles of nitrogen plus 0.11588 which we calculated moles of water. So this gives you the from this you can find out the new values of water present, oxygen and other components. So you have to do an again the balance of each component, each chemical element, so carbon, hydrogen and so on. So balancing that you will get the new equation. So here the only additional thing which will vary is the water vapor which we found previously. So we had 2.75 moles of water. So in this case it will be 2.75 plus the new amount of water which was present at the inlet. So from this we know how much amount of water is present at as a product. So from this you can find out the new molar fractions, and from there we can find out the partial pressure of water vapor in the product. So the new partial pressure of water vapor is 11.0176 kilopascal. So corresponding to this, your dew point temperature is 47.7 degrees Celsius. So if you see the humidity in the incoming air, so previously the dew point temperature is 44, now it varied to 47.7. So because of humidity, the dew point temperature increased by 3.7 degrees. So one more thing is required mass flow rate of air per kg of fuel. That we can easily find out. I think I have not added it here. So that is nothing but your total mole of air divided by mole of your fuel into your molecular weight of fuel by molecular weight of air. So that you have to convert these moles into mass, and you have to just take a mass ratio. So they are just asking for a air fuel ratio, so that can be found out. So we know moles. So for 1 mole, and you have 1.85 into 3.1667 into 1 plus 3.76 plus 0.11588. So that is the air. So into your molecular weight of air, molecular weight of fuel divided by molecular weight of air will give you the air fuel ratio in terms of mass. Any question in previous problem? Okay. So moving on to next question. A hydrocarbon fuel with chemical formula. Hydrocarbon fuel with chemical formula CnH1.87n. So it says you have n numbers of carbon, corresponding you have 1.87 times of hydrogen. So this undergoes combustion with a certain amount of air. It is noted that combustion of 1 kilomole of fuel produces 49.047 kilomoles of nitrogen and 1.3044 kilomoles of oxygen. Determine the combustion of the fuel and the equivalence ratio. So they have given the product. So they are saying that it contains 49.047 kilomoles of nitrogen for 1 kilomole of fuel which is getting combusted, and you have 1.3044 kilomoles of oxygen. So we know two components. So we'll see how to find this. So we need to find out N to find out the composition of the fuel, and we need to find out the equivalence ratio. So first we'll write a general equation. So we know the fuel is CnH1.87N. So if it goes into complete combustion, so you have stoichiometric ratio of air. So you use B moles of air, which gives you, if you do in carbon balance, so if you have N moles of CO2 plus you have some water and nitrogen, so you will have B into 3.76 moles of nitrogen, and then 1.87 N by 2 of water. So if you do balancing, so the question it's said that 49.047 kilomoles of nitrogen is present and 1.3044 kilomoles of oxygen is present. So from there, if you do in balance, you will find out that your fuel required is 1.4675 times of N. So now we know how much amount of air is required. So if we substitute again in the expression, and the equation, we are modifying the equation. So so now we found out B. So we are substituting B in the expression. So this what the new expression will be. So we are dividing it by 5. So to make it you're saying you have excess amount of air. So the phi is the equivalence ratio. So equivalence ratio is nothing but your stoichiometric air fuel ratio divided by your actual air fuel ratio. So for one, you are assuming 1 mole of fuel. So it's just nothing but mass of air, a stoichiometric mole of air divided by your actual mole of air. So hence you are dividing by equivalence ratio throughout in the above equation. So this will result in additional moles of nitrogen and oxygen being present. So when you write a new balance, chemical balance, so this is what you will get. So you have 1 mole of fuel plus 1.4675 N, which is the stoichiometric air moles of air required, divided by 5 is the actual air which is produced. So this results in same amount of carbon dioxide plus 1.87 N, the same amount of water, and you have nitrogen. So the new one is 5.5178 N by 5. So this is the excess nitrogen which is present, the actual amount of nitrogen which is present, plus you do an oxygen balance. This is what you will get, 1.4675 N into 1 minus 5 by 5. So this is the amount of oxygen which is present. So now in the question it is given as nitrogen present is 1.3044 and oxygen is 1.3044 and nitrogen is 49.047. from this we can find out the both equation has unknowns n and phi, and we know we have two equations. So 5.5178 by 5 into n is 14.047, and similarly for oxygen we know the moles present. So correspondingly we have two equation and two unknowns. So we solve this, we will get n as 8 and phi as 0.9. So we can substitute this in the fuel formula, and you can get the composition of the fuel. So any question in this? So what we did is, first we wrote an stoichiometric equation, and if you balance this equation, so if you balance this with respect to oxygen, so what you will get is 1.4675 n, B equal to 1.4675 n. So that is the stoichiometric mole of air which is required. So you are substituting that, and then now you are assuming that you are taking an actual balance of air. So your actual moles of air, you are writing it in terms of equivalence ratio, and then again balancing the chemical equation, reaction equation. You are getting new nitrogen and oxygen moles present at the products. So you are equating that with the values given in the problem, and you have two unknowns and two equations. From there you can find out what is the corresponding value of n to find out the composition, and phi equivalence ratio, which is asked in the problem. Okay. So next is determine the enthalpy of formation of gases methane, acetylene, ethylene, CO2 and CO. Assume the enthalpy of formation of carbon which is in gaseous form from the element solid form to be 0.7184 into 10 power 6 kilojoule per kilomole. So this is 10 power 6, so kilojoule per kilomole. And here in the table they have given for each bond how much energy is required. So hydrogen bond has energy of 0.436 into 10 power 6. The carbon bond is 0.348 into 10 power 6, and so on. So you have carbon double bond, carbon triple bond, and carbon with oxygen, all is given. So we'll see how this you can find out what is the enthalpy of formation of gas using this data. So first is for methane, so CH4. So this contains 4 moles of 4 carbon bonds with hydrogen, and there is a formation of carbon from solid to gaseous, and this we need to break hydrogen bonds. Hydrogen is 2, it will be formed in H2. So you have C plus H2 which forms CH4, and you require 2 moles of hydrogen H2 for 1 moles of carbon. So you need to break 2 H2 bonds and form 4 CH bonds. So for breaking bonds, it will release this amount of energy, and forming it will consume that amount of energy. So forming you are putting in negative, and breaking you are putting in positive. So from solid to gaseous, the energy is 0.7184 in 10 power 6 plus the hydrogen bond which is broke. So 2 moles into 0.436 into 10 power 6, which is the hydrogen bond energy, and you have carbon hydrogen bond which is 0.413 in 10 power 6. So minus 4 moles, 4 bonds of carbon hydrogen. So 4 into 0.413 into 10 power 6. So this will come out to be minus 61600. So but if you see, the actual value is minus 74850 kilojoule per kilomole. So this is just an estimate which we can find. So this difference is occurring because of other energies which is associated with the molecule. So similarly, next one, acetylene. You see acetylene has C2H2, so you have one carbon and hydrogen atom, two carbon hydrogen bonds, and C triple bond C is present. So similarly for this, you have to convert solid to gas carbon. Then you need to break one hydrogen atom bond. So and you need to form one carbon triple bond and two carbon H bonds. Similarly, if you take that values, so 2 carbon CH bonds, so minus 2 into 0.413 into 10 power 6. So this is formation, so this is consumed energy, minus 0.814 into 10 power 6, which is the C triple bond C. So C triple bond C, 0.814 into 10 power 6. Then similarly for hydrogen atom, 0.436 into 10 power 6 plus 2 into, you require 2 carbon atoms, so 2 into 0.784 into 10 power 6. So this will give you 232800. So if you see, this is very close to the actual value, which is 226736. Next is ethylene. So ethylene is C2H4. So this contains one C double bond C and 4 CH bonds. So for 4 CH bonds, you need to break 2 hydrogen atoms and you need 2 carbon. So minus 4 into CH bonds, number of CH bonds. So minus 4 into 0.413 into 10 power 6 and minus 0.615 into 10 power 6 is the C double bond C energy which is consumed, plus 2 hydrogen H2 bonds which you are breaking, 2 into 0.436 into 10 power 6 plus 2 into 0.7184 into 10 power 6. This is the carbon. So this gives you similarly for 41800 and the actual value is 52470. So this method gives you fairly estimate of the enthalpy of formation. That actual value can be found out from the table. So this just to show how we can get a reasonable value. So next is CO2. So CO2 contains two COO bonds. So 2 atoms of an oxygen you have to break one O2 bond. So CO2 contains minus 2 into the CO bonds, C double bond O bonds. So minus 2 into 0.804 in 10 power 6 plus the oxygen bond, which is 0.498 in 10 power 6 plus the carbon 0.7184 in 10 power 6. So gives you minus 391600. So if you see, this also is very close to the actual value, minus 393510. Next is carbon monoxide. So carbon monoxide, the carbon atom is joined to the oxygen atom by triple bond. So hence the enthalpy of formation for CO is minus you can take 2 carbon atoms and 2 oxygen atoms and divide by 2. So the formation of CO C triple bond O bond, so minus 2 into 1.07472 into 10 power 6 plus the oxygen bond breaking value 0.498 into 10 power 6 plus 2 into 0.7184 in 10 power 6 divided by 2. So this gives you minus 104600 kilojoule per kilomole. Actual value is minus 110530. So if you see, that is also is reasonably close. So here the negative value indicates that heat is released because of formation of CO and CO2. The next question is we have a liquid N-dodecane. So if you see the formula for liquid N-dodecane is C12H26, which is at 298 Kelvin, and air at 700 Kelvin steadily enter the combustor of a gas turbine engine. So you have fuel at 298 Kelvin, the composition of which is C12H26, which is combusting with air at 700 Kelvin. So determine the required mass flow rate of air and the corresponding equivalence ratio. if the temperature of the products is 1700 Kelvin and 2200 Kelvin, so heat loss from the combustion may be neglected. So the enthalpy of formation of liquid endodecane may be taken as minus 352100 kilojoule per kilomole. So we'll see how to solve this. So if you see, this is how the equation will be for the complete combustion. So C12H26, which is in liquid form, plus 18.5 into oxygen plus nitrogen, the air, gives you 12 moles of carbon dioxide plus 13 moles of water plus similarly 18.5 into 3.76 moles of nitrogen. If excess air is supplied, so if you see x amount of excess air is x moles of excess air is supplied, so 1 plus x into 18.5 gives you the new equation will be 12, same, carbon dioxide and hydrogen will be same. You have x amounts of x into 18.5 moles of oxygen which is present in excess, and 1 plus x into 18.5 into 18.5 into 3.76 moles of nitrogen. So now if you do an energy balance in the across the combustor, so you have there is no heat transfer from the combustor, so Q is 0 and work will be 0. It is just reactant and product. So you have enthalpy of formation of your fuel plus your delta H change. This is the sensible heating from the formation temperature to the temperature at which the fuel is set. So here they are giving at the same temperature 298 Kelvin, so this will be 0 plus 1 plus x into 18.5 moles of air, so corresponding air enthalpy of formation and sensible heating. So here enthalpy of formation of oxygen and nitrogen is 0 at 298, so that is 0, and your sensible heat this thing value should be taken because the air is at 700 Kelvin, then minus your product, so minus 12 into the product, so minus into product enthalpies, so 12 into carbon dioxide, so similarly formation and sensible, and 13 into similarly hydrogen outside water, and then 1 plus x into same for nitrogen and oxygen. This is at the product temperature which is given for two temperatures which we have to consider. So from this we can find out x. So this is equal to 0, so the one here we can write x in terms of the enthalpy values. So if you write x, x will become 12 times your sensible heating of CO2 plus 13 into your sensible heating of water plus 69.56 nitrogen minus 8577.391. So this is all combining your formation enthalpies. So your CO2, your water, and then fuel. So this is what you get, minus 85.577.391. This enthalpy of formation value, you can take it from any book, the table they are given in the appendix, so you can see that and take the values and divide by x into your nitrogen and oxygen plus your air values. So now we know the x value for we need to find out the corresponding the sensible enthalpy values for each component at the product temperature and substitute here. From there we can find out the what amount of air should be supplied. So for initially for first case of your product temperature of 1700 Kelvin, you can solve for x from substituting all this sensible enthalpy values from the table, and it will come out to be 1.2695. So x is 1.2695. So the mass of air which will be required is 1 plus x into 18.5. So from the problem, so 18.5 into 4.76 moles of air. So oxygen 1 plus 3.76 nitrogen into your molecular weight of air, which is 28.84, because this is moles, we are converting into mass, so 28.84 divided by your molecular weight of fuel. So molecular weight of fuel, we know 12, so 12 into carbon 12 plus 26 into 1, so 144 plus 26, so number 170, so divide by 170. So we substitute x value and we'll find out that mass air fuel ratio for per kg of fuel you require 33.905 kg of air. So from this now we can find out the equivalence ratio. So equivalence ratio is nothing but stoichiometric air fuel ratio divided by actual air fuel ratio. So stoichiometric air fuel ratio is 1, and because we took 1 plus x times of your stoichiometric ratio, so 1 divided by 1 plus x, so we know x value, substituting that we find out equivalence ratio is 0.44. So next is we need to find out the correspondingly same values when your product is at 2200 Kelvin. So similarly we will find out the sensible enthalpies for each of the component, substitute in the previous equation for x, and find out the new x is 0.4032. So similarly substituting for mass of air, we will find out mass of air required is 20.9626 kg per kg of fuel, and for that mass your equivalence ratio is 0.7127. Any question in the previous problem? Okay. So determine, the next question is determine the higher and lower calorific value of methane at 298 Kelvin. Assume the enthalpy of formation of methane to be minus 74,850 kilojoule per kilomole. So again for methane we will write a stoichiometric amount of air, what is the complete combustion equation we look like. So 1 mole of methane it requires 2 moles of air, which gives you carbon dioxide plus 2 moles of water, which is in vapor form, plus 2 into 3.76 moles of nitrogen. So if you write a steady flow energy equation across the combustor, so this is what we did in the previous problem. So Q divided by number of moles plus your enthalpy formation of product reactant plus sensible heat for your methane plus air, similarly for air, and then your here in the problem we are assuming that methane and air are all at 298 Kelvin. So your enthalpy formation of air and sensible heating of air is also 0. So enthalpy of fuel is also 0. So minus your product, so enthalpy formation of carbon dioxide plus your carbon dioxide and other component. So first we will find out your lower calorific value. So this will come out to be minus Q by N dot F is equals to, we substituting all the formation values and taking it to the other side, we will get 802330 kilojoule per kilomole of fuel. So this is the calorific value of the fuel. So if you convert this into mass basis, so dividing by the molecular weight of fuel gives you 50146 kilojoule per kg of methane. So similarly higher calorific value is nothing but your you need to take into account the condensation of vapor, your water vapor. So if you do that, you will have the enthalpy latent heat of water vapor, which is also come into the calorific value. So similarly for fuel, then carbon dioxide and then water water vapor, you take minus 2, 2 into your formation of water minus 18, which is the molecular weight, into your latent heat at 298 Kelvin, so 2441.55. So if you substitute that, so you get higher calorific value as 890226 kilojoule per kilomole of fuel. And similarly, if you divide it by molecular weight, you will get in terms of kgs, so 55639 kilojoule per kg of methane. So the only difference between lower calorific value and higher calorific value is, in a higher calorific value, you will also take into the value of heat which you obtain from condensation of water vapor. So the next question is, you have C4H8 which is burned in an engine with a fuel rich air fuel ratio. Dry analysis of the exhaust gives the following volume percent. So your CO2 is 14.95%, your fuel is 0.75%, CO is 0%, H2 is 0%, oxygen is 0%, with rest being your nitrogen, say N2. Higher heating value of this fuel is 46.9 megajoule per kg. Write the balanced chemical equation for 1 mole of this fuel at this condition. You need to calculate air fuel ratio, equivalence ratio, lower heating value of the fuel, energy released when 1 kg of this fuel is burned in the engine with a combustion efficiency of 98%. So first, we don't know how much amount of fuel which is burned, so we will take that as some x. So x amount of fuel is burned, and it has y amount of air present. This gives you 14.95% of carbon dioxide, 0.75% of fuel, plus 84.3% of nitrogen, and Z% of water. So here too you are doing a dry analysis. So you have 14.95 minus plus 0.75 is the minus 100. So that is what the amount of nitrogen which is present. So that is 84.3. So now if you balance carbon, oxygen and nitrogen, so if you do nitrogen balance, so y into 3.76 equals 84.3. From there we will find out y is 22.42. So you require 22.42 moles of air. So similarly for you, if you balance oxygen, so you will get Z. So 2 into 22.42, which is on the reactant side, into 2 into 14.95 plus Z moles of that oxygen present in water. So this gives you Z as 14.94. Then if you balance hydrogen, or you can balance a carbon, any of which, so you will get 8 into x equals 8 into 0.75 plus 2 into 14.94. This gives you x as 4.485. So this from this we can find out the actual reaction equation. So 4.485 moles of fuel with 22.42 moles of air combust to form 14.95 moles of carbon dioxide, 0.75 moles of fuel plus 84.3% of nitrogen plus 14.94% of water. So if you divide this with respect to the mole of fuel present, so per moles of fuel, so you have the modified equation which you will get. So 1 mole requires 5 moles of air, and you have product. So if you write air fuel ratio, this is nothing but mass of air divided by mass of fuel. So mass of air you can write as mole of air into molecular weight of air divided by mole of fuel into molecular weight of fuel. So this gives you 5 into 4.76 into 29 divided by 1 into 56. So 56 is the molecular weight of fuel. So 4 into 12 plus 8. So we'll get 56. So substituting and calculating, we'll get air fuel ratio as 12.325. So if you write a stoichiometric reaction equation, so this is how it will be. So 1 mole of fuel requires 6 moles of oxygen. So if you see in the previous problem, you had a less air, so there was not complete combustion, so you had some amount of fuel which was left. So in this case, you are doing a complete combustion, so you have 1 mole of fuel which is getting completely converted. So plus you require 6 moles of air for that, and it gives you 4 moles of CO2 plus 4 moles of water plus 63.76 moles of nitrogen. So from this, similarly, you can find out the air fuel ratio. So 6 moles of air into 4.76 into 28 molecular weight of air divided by 1 into 66 gives you 14.79. So your equivalence ratio is stoichiometric air fuel ratio divided by the actual air fuel ratio. This comes out to be 14.79 divided by 12.325, which is 1.2. So this says that it is a rich mixture. You have fuel rich and you have less oxygen, so less air. Your equivalence ratio is less than 1, that means you have excess air. Now we need to find out the lower heating value. They have given the higher heating value. So you need to find out what is the energy which you are getting from condensation of water. So for 1 mole of fuel, you have 4 moles of water forming. And here for calculating heating value, you use the stoichiometric equation, not the actual equation which is in the problem, because that will give the overall total heating value. So for that, you need to take into account the complete combustion. So for 1 mole of fuel, you have 4 moles of water which is formed. So 4 into the molecular weight of water into your latent heat at 298 Kelvin or 25 degrees Celsius gives you 175.85 megajoule. So this is your latent heat of due to condensation of so your lower heating value is higher heating value minus your because of water latent heat. So if you in the problem they are given higher heating value in terms of megajoule per kg of fuel. So similarly, you need to divide by molecular weight of fuel, because we have found out 175.85 megajoule per kilomole of fuel. So we need to divide by molecular weight to convert it into kg. So you get 3.1 megajoule per kg. So from this you can find out your lower heating value as 43.8 megajoule per kilojoule. Sorry, megajoule per kg. So the next was to find out for 98% efficiency what will you get. So for if you take 1 kg of fuel, so 1 into you have 43.8 megajoules into 0.8 and 98 will give you 42.9 megajoule. That is the amount of heat which you get for 98% combustion efficiency. Any question in the previous problem? Then moving on to the next problem. A stoichiometric mixture of methane and air at 298 Kelvin enters an insulated combustor where it undergoes complete combustion. Determine the temperature of the product leaving the combustor. So till now in the combustion process we found out what is the amount of air which is supplied, and for the given amount of given temperature of product. So that's what we saw in one problem, and then we saw how much heat will be generated. So in this case, now what we are seeing is we need to find out the product temperature. So what will be the product temperature will be when you are insulating the combustion. So there is no heat lost. So in that case, here your fuel is methane. This is at 298 Kelvin. So we'll see how to solve this. So you have combustion of methane with a stoichiometric amount of air. So CH4 plus your 2 air requires 2 moles of air, which gives you CO2 plus 2 moles of water vapor plus 2 into 3.76 moles of nitrogen. So if you write a steady flow energy equation, so this is what you get. So you have Q into N dot by 4. So this being insulated, this is 0. You see in the previous problems, in this for finding calorific value, you didn't assume Q as 0 because you are that fuel is combusted to take that energy, to provide that energy. So this is not insulated. So you have Q here, but your products is also at 298 Kelvin. There. Here the products will be at different temperature. So that is the difference here. So if you write a steady flow energy equation, this is what you will get: Q by moles into your enthalpy of products minus enthalpy of reactants. So again, enthalpy of products is the enthalpy formation of methane plus sensible heating of methane. So here that is at 298 Kelvin. So this is 0. And similarly for air, so air formation enthalpy is 0, and your air is also at 298 Kelvin. So that is also 0. And then the enthalpy of products minus enthalpy of products. So enthalpy formation of CO2. Since the product temperature will be higher, this being insulated, there is no heat rejected to ambient. So this will products will be at higher temperature. So it will eat up themselves. So the product will be at higher temperature. So you need to take into account that. So plus delta H of CO2, the sensible enthalpy, and then for water similarly plus and nitrogen. So now if you see, this can be written in terms of the sensible heating components of the product. So enthalpy formation of methane from the table you can find out, and similarly enthalpy formation of carbon dioxide and water can be found out. So substituting that and taking it to the other side, you can find out what is the sensible enthalpies for the products. So you have delta H CO2 plus 2 times delta H of H2O plus 7.52 moles of nitrogen into delta H N2. This is equal to the total enthalpy of formation, so 802330. So this is the equation which you get doing a steady flow energy equation. So now the temperature, we have to find it. We don't know the temperature, so we will assume some temperature and we'll find the corresponding sensible enthalpy values from the table, substitute here and see if we are getting the same value 802330. So if it's not, then we have to assume some other value. So we know that this is at 298 Kelvin, and we are assuming that this should lie between somewhere 298 and 3000. So we are taking doing a binary bisection method. So we have two values, we will take the midpoint. So 298 plus 3000 divided by 2, we have 1649 Kelvin. So correspondingly our guess value at start is 1649. So in the table we have 1700, so we take 1700 nearest value, and from the 1700 we see substitute to the enthalpy values, and we see that enthalpy value is 52 9731, and the actual value is 82330. So if you see, this is smaller, so your enthalpy formation is less, so you need a higher temperature. So next you will take a higher value, so you can take 1700 and 3000 the divide by 2, so you can take 2350, so closest 2400. So if you see there, your enthalpy value you are getting is 833440. You see, this is higher than what is required, what is there. So your temperature is lesser than 2350. So if you see, assume 2330, sorry 2300. So correspondingly your left hand side will come out to be 789177. You see, this is less than the required, and but it is your value which you require is lying between the last two values. So your temperature will also lie between 2350 and 2300. So now you can do an interpolation and find out what is the temperature. So if you do an interpolation, you will see your temperature is 2330 Kelvin. So your product will be at 2330 Kelvin. So any doubts in this? What we did is we wrote an stoichiometric energy chemical reaction. We did a steady flow energy equation for the combustion, and we substituted the formation values, and the only unknowns were the sensible enthalpy values which you get, and that we can find out only based on temperature. And so we assume temperature, we get the values and see, cross check if we are getting the same value. If it not, we correspondingly take higher or lower temperature value and bring this closer, and we found out that your temperature you require is 2330. So the next question is a stoichiometric mixture of N-octane vapor and air at 700 Kelvin and 1000 kilopascal undergoes combustion in the cylinder of a spark ignition IC engine. Assuming the combustion to occur at constant volume and neglecting heat loss, determine the final temperature and final pressure. The enthalpy of N-octane vapor at 700 Kelvin may be taken as minus 94,880.75 kilojoule per kilomole. So we have stoichiometric mixture of octane vapor, which is at 700 Kelvin and 1000 kilopascal, which is going into combustion in an IC engine. So we are now this combustion is happening at constant volume, and we are neglecting heat loss. So there is no heat loss. We need to find out the final temperature and pressure. So we'll see how to solve this. So since combustion is occurring at constant volume, so this change in energy of system is change in your internal energy. So your internal energy U is product is equals to the U into reactance. So previously what we did is we balanced the enthalpies here, because this is at constant pressure. Now it's occurring at constant volume, so we are equating the internal energies. So your product internal energy is equal to the reactant internal energy. So combustion of N-octane, the stoichiometric ratio of air can be written as, so octane is C8H18, which is in vapor form, plus it requires 12.5 moles of air, which gives you 8 moles of carbon dioxide, 9 moles of water vapor, and 47 moles of nitrogen. So now we can write balance the internal energies. So your enthalpy can be written as U plus PV. So PV you can write as nRT. From idle gas, you can assume this is idle gas. So this you are writing specific enthalpy equal to specific enthalpy. So this will be equal to plus RT. So you can write enthalpy as U plus RT. So from this you can find out the internal energy as enthalpy minus RT, and R is the universal gas constant. So this reactance is at 700 Kelvin, and we need to find out the product pressure and temperature. So your right hand side has the product, so left hand side has product, and right hand side you have reactants. So 8 HCO2 minus RT plus 9 enthalpy of water minus RT plus 47 enthalpy of nitrogen minus RT equals your fuel plus air, which is at 700 Kelvin. So this enthalpies can be again written in terms of the formation and the sensible. So this out the new reaction will be 8 delta H CO2 plus 9 delta H2O plus 47 your nitrogen minus 64 RT, 47 plus 9 plus 8, and this is equal to your enthalpy of fuel plus 12.5 delta HO2 plus 47 delta HN2 minus 60.5 into RT minus your enthalpy of formation of carbon dioxide and water. So if you know the right hand side values, you know the enthalpy of formation of the components and the fuel, and you know what temperature your fuel and air is at. It's at 700 Kelvin. So corresponding your enthalpy values can be found out from the table. So substituting that, we will get delta H CO2 plus 9 delta H H2O plus 47 delta H N2 minus 64 RT equals 55 96206. So now similar to the previous problem, we will assume some temperature and try to find out the temperature of the product. So similarly we start with 1649, so the nearest is 1700, so we get the left hand side as 2332 687. So if it is way off from the actual value, so you take 2350, it gives you 2400 nearest value, it comes out 3806530. Again this is very different from what is required, so you will less than the required value, so you take a higher temperature value, 2650, so that gives you nearest is 2700, so that is 59791. So even now this is even less, so now you take 3000, so if you take 3000 you get 5121512. Now also it's less, so you have to take a higher value, so now you are taking 3500, so if you take 3500 you are getting 6234764. You see that is higher value than what you require, so your value should lie somewhere between 3000 and 3500. So if you take 3200, what you get is 5564 593. See, if you see, that is close to what you require. So if you do an interpolation, you can find out the actual value is 3213 Kelvin. So now you know the temperature, you need to find out the pressure. So because this is occurring at constant volume, so initial P by T is equals to the final P by T, because constant volume. So P equals to the final P by temperature, which is 3213, equals 1000 kilopascal initial divided by 700. So your P can be written as 1000 into 3213 divided by 700, which gives you 4590 kilopascal. So this is the final pressure of the product. Any doubt in this problem? Okay. I think this is the final problem which I prepared. So we'll see how to solve this. So till now we did an enthalpy balance. We will also see an entropy balance now to find out what is the entropy which is generated during combustion. So propane enters the combustor along with 200% theoretical air steadily at 298 Kelvin and 100 kilopascal. So propane is combusting and it is 200%, twice that of stoichiometric air which is required is supplied at 298 Kelvin and 100 kilopascal. The product of combustion leave at the same temperature and pressure determine the entropy generated. So your product is also living at 298 Kelvin and 100 kilopascal. Take the enthalpy of formation and entropy of propane at 298 Kelvin to be minus 104700 kilojoule per kilomole and 270 kilojoule per kilomole Kelvin respectively. So we'll see how to solve this. So combustion of propane with stoichiometric air may be written as, so propane is C3H8. So you write a stoichiometric reaction. So you have C3H8, 1 mole of propane requires 5 moles of air, which gives you 3 moles of carbon dioxide plus 4 moles of water plus 18.8 moles of nitrogen. So now you are supplying twice the stoichiometric air mole, so 200%, so twice. So C3H8 into 10 moles of air, because initially in stoichiometric you have 5, so this you will get supply 10. This gives you same amount of carbon dioxide, 3 CO2 plus 4 H2O. Now you have 5 moles of air which is coming out without combustion, so 5 O2 plus 37.6 nitrogen. So now if you do in energy balance, your reactants and products are at same temperature and pressure, so the heat is getting rejected. So we can find out Q per moles of fuel. So Q by N dot F equals reactant minus product. So this gives you 3 into reactant is formation of carbon dioxide plus formation of hydrogen water minus formation of propane, because this product and reactant are the same temperature and pressure. Because the reactants and products are at same temperature, because the reactants and temperature and pressure, reactant and products are at same temperature and pressure, there will be no sensible enthalpy heating which is happening. So you have just formation enthalpies. So this gives you minus 2043,180 kilojoule per kilomole of fuel. So now what we'll do is we'll find out the corresponding mole fractions of reactants and products. So in reactants you have oxygen, nitrogen and propane which is present. So oxygen mole is 10, nitrogen is 37.6 and fuel is propane is 1 mole. So if you take corresponding mole fractions of reactant, you have mole fraction as 0.2058 for oxygen, 0.7736 for nitrogen, 0.0206 for propane. So if you add up, you have 48.6 moles of reactants, and mole fraction should come out to be 1, so that's what you get. Similarly for products, if you see, you have oxygen, nitrogen, carbon dioxide and water. So from the equation you can write out how many moles are present. So oxygen is 5 moles, 37.6 moles of nitrogen and 3 moles of carbon dioxide and 4 moles of water. So correspondingly, what is the mole fraction is 0.1008 for oxygen, 0.7581 for nitrogen, 0.0605 for carbon dioxide and 0.0806 for water. So if you see product, you have 49.6 moles of the product, and mole fraction should be 1, so that's what we get. So we'll see how to do an if you do an entropy balance. So entropy balance is product minus reactant plus the Q by T is equal to the entropy generated. So this is an entropy balance if you see. So we need to find out, we have found out how much heat is rejected, Q dot by N we have found out. You know the temperature, which is at 298 Kelvin, your surrounding is at 298 Kelvin. So we need to find out the products entropy and reactant entropy. So first we will see the reactant entropy is reactant entropy of propane plus entropy of air. So if 1 mole of propane, so 1 into entropy of formation, entropy at 298 Kelvin minus R into your entropy of mixing, so minus R into ln of your mole fraction. plus similarly for 10 moles of oxygen into entropy of oxygen at 298 Kelvin minus R into ln of your oxygen. So this, if you see, it's nothing but your partial pressure by actual pressure. From Dalton's partial pressure, you get mole fraction. So minus R ln of oxygen, molar fraction. So minus R ln mole fraction of oxygen plus 37.6, and similarly for nitrogen. So we substitute all the values. So from the table you can find out entropy values for oxygen, nitrogen, and propane is given, and we have found out the mole fractions. So substituting, we will get entropy of reactant as 9770 kilojoule per kilomole Kelvin, kilomole of fuel into Kelvin. So product is similarly 3 into entropy of carbon dioxide plus 4 into entropy of water plus 5 into entropy of oxygen plus 37.6 into entropy of nitrogen. So similarly, like the previous one, we can find out the entropy values. So substituting your entropy values from the table and the mole fraction which you have found out, and R is a universal gas constant. So substituting that, you will get 9962.689 kilojoule per kilomole of fuel Kelvin. So if you substitute in the entropy balance equation, so entropy generated is entropy of product minus entropy of reactant plus Q surrounding by the number of moles in by your temperature. This is entropy because of the heat transfer. So we have substitute all the values. So you know the heat which is supplied. So 2043.180. So divide by 298, and reactant 9770, and 9962.689. So substituting that, we will get the entropy generated is 7049 kilojoule per kilomole Kelvin. So this is the amount of entropy which is getting generated. So any question, this problem you can ask, or in general any question you have regarding this lecture or the previous lectures, you can ask. I have finished what I prepared for today. If you have any doubts, I can clear that. Okay, so if you have no doubts, then we can end the session, and next also this Wednesday there will be a review session. We are going over your classes. So today week lecture I will take it on Tuesday, and Wednesday same time I will take it 6 o'clock. I'll do a
So
review session.
Wednesday, sorry sir, Wednesday the revision will be for all the chapter, right sir?
Yeah, all chapter combined, and if you have any doubts in the problem, you can ask. I can clear that, or I'll come up with each week one problem or something. I'll come up and try to make one. I'll come up with 10 to 11 problems similar to what I do now. I'll come for a review session with all the problems.
Sure sir. If further again problem arises, then I will mail you. Okay sir?
Yeah, sure.
Okay sir. Thank you sir.
Yeah, thank you. See you in the next class.
Okay. Good night sir.